the community. Oops. I don't know why it did why on earth is it doing that? So in any case, I think the recording started. We are just going to, remember, switching gears to describe solids now. And as I said, there's no better place to get started than talking about the case of elastomeric state, okay? So we'll be discussing basically elastomeric state. That's certainly one example of having a solid. To discuss this properly, there's no way to escape some description about single chain behavior. So I will go through according to this outline that's updated, and quite a few of this content is unfamiliar in the literature or rarely discussed in the literature, certainly not in polymer physics book. So I thought this is something worth recording and start to share with the community. So I will start with, so let's get started, right? So we're looking at elastomeric state, and your mind could quickly form that we're dealing with something like this. To begin, we obviously, it seemed to me obvious that if I treat each of this strand as a Gaussian coil, I should start to first describe how I think about the deformation of this representative or test strand. You can call this a test strand, and then go beyond that eventually. So from what you are familiar with, the force is basically entropic in origin. So basically, you can think about this as nothing but differentiate an entropic component of the system with respect to the size, and the entropy of a system is like 3 kT, the size of the end-to-end distance squared divided by the average size of it. So there are notations I can use. For example, here we may use the notation that if you call this has an end-to-end distance of Lx, then this is nothing but Lx squared. X stands for cross-linking. So in any case, you will be able to find that this is something like linear in the size of the strand. I'm going to skip a lot of a detailed discussion, and I refer you to Rubinstein-Kolbe's book, for example, where it is mentioned that there is a way to think about going beyond Gaussian, meaning this merely says your force will linearly grow with the distance between I actually probably should be clear about my notations. I really mean R should be treated as Lx. Its averaged value. So in theory, it's a vector. So I'm not going to worry about that being a vector. Its average value is, what is my notation? I mean, really, you should be familiar. The average value is so-called this. It has to do with chain length and times cone length. So I kind of misspoken here in the sense that this term is nothing but and this. The familiar thing, the Gaussian chain behavior. So what happens is this is all fine if this chain remains a coil, okay? In other words, initially like this, and now it gets stretched a little bit more. That's still okay. But what if the chains are fully straightened? And eventually, well, if you keep stretching forever, you should keep building tension and eventually even break it. So, so the model that can describe this configurational change is called freely jointed chain model. This book talks about it, so I will not go into any detail except to indicate that any distance between end-to-end distance, if I call that R, I know I'm switching my notations back and forth. I hope not. I hope you are not confused by this. So basically, I'm taking a unit which is the strand. So that strand, according to this FJC model, relates the distance between the end-to-end to the tension that exists here. Okay, the tension that's in the chain. Here, maybe I can even switch back to a lower case, just like the Fx here is tension. We call this tension. Here, this tension is normalized by a quantity we call F0, which is of the magnitude of kT divided by cone length. So I'm not going to go through the details of how to derive this, except to share with you its behavior. And its behavior is given in the next slide. So if you plot that, this actually, you can see, don't get scared by it. I'm just going to do this. We call this inversion. So if you can invert this, this is so-called Langevin function, named after a French physicist. So you can invert that Langevin function and get the force. So this is just notational, symbolic. So you can invert it and write. And it turns out it's all doable. In fact, this can be approximated by R over R0 divided by 1 minus R over R0 to the third power. So people actually are crazy about this inverse Langevin function and propose many mathematical forms that approximates it. And this is one of it. It has a name, I forgot what it's called. But you can see, can you see that this function captures the fact what is L? L is when this chain is fully straightened. Let me carefully use the word L0, okay? Just for the sake of additional discussion. So if you're, forgive me, I'm switching back from using R versus using Lx. Okay, forgive me on that. Lx is just trying to acknowledge I'm looking at one strand, but generally I just have a chain, so I just want some simplicity. It doesn't, just take a chain. That chain, of course, will have a length, has the size of this. That's Gaussian coil. And then L0 is nothing but lined up all these cone segments, one by one. So if you like, this even introduces a concept called limiting stretching. You see, this coil can only stretch this much before it gets straightened, starting with R, going to L, 0. And this expression tells you it's nothing but square root of the chain length. So you already learned something quite new, this lambda star. It's the limiting stretching amount you can have. So it turns out if I plot this function, I can get f very trivially, which is next plot. The blue is that expression. The red is the Gaussian. The red is this one, meaning the red is like saying my f is simply I know I'm kind of it's in here, so I'm going to just so this basically, let me erase it. So basically, f for a Gaussian chain is nothing but some kind of constant times r. Okay, so that means that it's this red. It's going to linearly changing instead of this divergence. It diverges because it behaves as 1 over r0 to the third power. Okay, so it diverges at the 0 there. So this is classic. This is in Rubinstein and Kolbe's book. It says the force can keep building as you straightening the chain. One piece of information you may find useful is to have a sense of what is this F0. You can estimate. We do that a lot for the rest of our few weeks. Cone length characteristically is generally, you may just sort of treat it as something on the order of 1 nanometer. It's true for many of the linear flexible polymers. At room temperature, you know the value of kT. So F typically is something around 4 piconewton. Okay? Just to immediately have a sense of what's going on, a chain straighten, well, if you keep stretching, eventually, right? Eventually, it will break. That typically take a force on the order, let's call it breaking force, on the order of 4 nanonewton instead of piconewton, which is what? 1,000 times larger. The chemists should love it. We're talking about breaking the bond. So, this much is okay. I described a single chain. I described people have developed a description that can describe even when the configurational entropy is already finished. The force can still grow, can still further grow. And of course, this is for a single chain. You can actually build a model for it and write this for a network of such chains, or meaning such chains, meaning chains reaching, this is what is clearly so-called non-Gaussian stretching. Okay. And this is fairly unsatisfactory. Sometimes I mentioned this. I said, gee, this force keep building up beyond 4 piconewton. Since there's no conformational change, you see, when it's straightened, there's no more conformational change. So there shouldn't be any entropy to talk about anymore. It's all done. The rest of this thing straightened and still being stretched, very little amount being stretched, must involve stretching the bond now. Well, of course, people know that's the case. So people have developed the so-called modified freely jointed chain model. So before I teach you, I prepared to show you something about it in terms of demonstrating graphically what we're talking about here. So what we're talking about here is this is the freely jointed chain model. This part. This thing is called Langevin function. And then we invert it to get force as a function of the stretching. This is the bit that's added. Okay? And so this morning, I tried to graphically show you adding this little bit means what. The blue symbols in this plot, I should have the L0, I have it L0 there, is what we just showed, that Langevin expression, okay? The red is to add this term. While I only plot up to 50 times of F0, they are just on top of each other, okay? Well, so you do a little further. You go to a scale. Remember, this force is capable of being 1,000 times of L0. So, in fact, the model doesn't know, but you know. In fact, the chain by this time will break, more or less. I don't need to be exact. The model can plot it forever, but it will break. But look at now this different scale. The green, I didn't label it here. The green is that a freely jointed chain model. It's tiny because on this scale, 50 is nothing. Okay, so it's this part. It's already straightened, meaning your end-to-end distance has already reached L0. Not much is going on. The chain is straightened now. The rest, if you keep still wanting to stretch it, such as what you can do with AFM, if you properly anchor your chain to one end and make sure you can hold it and keep stretching, the force will be further build up. This model would say, and I think it's not terribly bad, it will say it will grow linearly. Okay, so beyond L0, you see, depending on how I assume this term, I just give a notation of F star. Depending on how I think about this F star, if I choose F star, okay, if I choose F star to be F0 times what? Times 3,000 times 30,000. Is that 30,000 or 3,000? Actually, it should be 3,000. Yeah, 3,000. That's about there. So basically, I'm just flipping this. Okay, so F star is F0 divided by 3 times 10 to the 4. Okay, that's all it is. Then I get this blue line. Otherwise, if I think my polymer is a little stiffer, then it wouldn't, the bond is stiffer. That bond, you see, you have so many bonds. Each bond will stretch a little bit, which allows it to stretch a little beyond L0 now. Because L0 is here, it's denoted as 1, right? Then I can travel to either, this is stiffer, this is softer, depending on which one. You will build the same amount of force depending. So this is just a illustration as a physicist to show you how this can happen. And when I say this line is because the force at this point will be very high, and you will break the chain, and you will never achieve 3,000 of F0. 3,000 of F0, if you take F0 as 4 piconewton, 3,000 of F0, which is this line, of course, will be 12 nanonewton, which is too high. Your carbon-carbon bond breaks before the stress level, force level. Any questions so far? This is just something I start to spend time on it because it is helpful for us to understand eventually the solid behavior, in this case elastomeric behavior at large deformation. So we will proceed. I will proceed. The next thing we should worry about, I know my notes is here, but I may have to rearrange it slightly. The next thing we should worry about is this, is how about breaking the chain, right? Okay, how about breaking the chain? This is your carbon-carbon bond, your backbones. So you can think about any bond between your two monomeric units connected by a carbon-carbon bond. And you can ask about how strong is that bond. And it turns out conveniently you can use a Mohs potential to describe it. Any potential will do to capture this feature of what you find this bond to be in. Basically, this bond is in a potential it sits there with a huge barrier to cross. So that barrier, we call it dissociation energy barrier, DE. Then, according to what is associated with names of Kaufman and Eyring, we can definitely think about the lifetime of a bond. In fact, the way I use the notation is such that I have, it's trivial to find, is I have gas constant here. And E for a carbon-carbon bond, which is the only thing we can talk about, according to density functional theory calculation by Beer, this is 370.8 kilojoules per mole. Okay? And in this formulation, T0 typically is regarded as the vibration frequency of the bond, dictated by KT divided by I think I'm doing it wrong. I think I'm doing it wrong. It should be H divided by KT. Okay. I think that's the only way that I can get the units right, because this H is nothing but Planck constant. Planck constant times frequency has the unit of energy. Okay, so this expression essentially it's a expression of ratio of two energies. So in any event, if I'm right, I don't have time to calculate for you. This T0 is something around 10 to the minus 13 second. Okay? Given this number, given RT at room temperature is 2.473 joules per degree, joules degree, you get a number which is very large, longer than the age of universe. Of the known, known age of the universe. So suppose, well, don't ask me. I have any opinion on it. This is what textbook knowledge. I'm not going to do anything about it. But Kosman and Eyring in 1940s proposed that bond, if you have enough force, you can break that bond. So, which means I can lower the barrier. So this is what I plotted for you. So let's ignore this part. We'll come back to it later, I think. Let's focus on this diagram, this figure. Let me try to spend all the time I need to go through this for you. So basically, what I plotted is the following. The red line, I want to emphasize the understanding of this bond association and dissociation, which is breaking, can be qualitatively described. Here I used Mohs potential to describe it quantitatively. And the Mohs potential basically says your bond is trapped in a potential meaning your bond at equilibrium is sitting here such that you can call that to have energy of 0. And to dissociate, to break, means you have to stretch until the corresponding energy is dE to break it. And as I said, that if you don't have any force, takes forever to happen. Okay, that's what we knew before. Cosmic iron suggests that if you have force, the barrier can be lowered. So here I plotted 3 different force levels to show you. For you to make sense out of this, I did one thing first. In this potential that bonds the 2 monomer together, a carbon-carbon bond, this potential whose derivative, so remember your bond is at some equilibrium distance with each other. Let's call that equilibrium such that only any extension you have a positive R, so meaning extending beyond 0. Once it's start to stretch beyond the equilibrium, you will sense a force. And that force is trivially prescribed by the potential energy by differentiating it. Right? It's under, it's like the free energy concept. And there's a maximum in this particular mathematical expression around here. There's a maximum slope for which you can, by definition, assign a maximum force. Fair? At this point. This point actually turns out to be this quantity equals log 2, which is about 0.7. So this is expressed in a dimensionless form. So in any event, this maximum is what I used to normalize. So what Kaufman and Eyring suggested that is once you have a force, this bond is sitting in a new potential given by what the force is. So maybe there is a bit of detail I will skip, but generally what I can indicate to you is this. If you have a force, according to them, try to stretch this carbon-carbon bond, and that force I can characterize in terms of normalizing it with the maximum. Then I can make such a plot. So it turns out this maximum force has the meaning that will become clear very soon. For example, if you really have a force reaching a maximum, your bond lifetime instantly goes to that of T0, which is 0.1 picosecond. In our lifetime, in our experiment, we can consider that to be instant. So in other words, if you apply force as much as F max, your bond will instantly break. What is F max? According to F maximum, according to density functional theory of Bayer, this force for carbon-carbon bonds is 6.9 nanonewton. Okay? So if you are able to provide that much force, it will break. Well, in reality, before you can apply that much force, the bond would already break because bond would not, you cannot detect tens of nanonewton, 10 to 1/10 of a picosecond. So in any case, once I normalize that, that's my F bar. Then I can start to indicate the mathematical consequence of this. The consequence is this. I illustrated using 3 different F bars. If F bar is 0, then this is where eventually have the barrier. It takes a long time to break. If I start to apply a force of 70% of the maximum, then the calculation basically shows that the black is the effective potential to confine the bond. And the barrier height now is only this much. Similarly, if I did it for 40%, the barrier height will be this much. If I only had 20% of the maximum force, my barrier height will be that of orange, it will be this much. So how much of the barrier height I have is analytically actually given by this expression, where the F prescribes the height of the barrier. Okay? In fact, this graph plotted that, normalized by the original barrier height, the red curve. And if you play enough with it, you find that this red curve can be easily approximated by a quadratic function. I do not know literature has mentioned this or not, but I fit it into a quadratic because this thing looks parabolic, inverted parabolic. Meaning parabolic with the origin shifted to 1. And I'm going to skip the rest of it about the fact that you can even try to linearize it in certain region. Okay, this is basically the feature. The part let me reiterate, it shows that by the time you use maximum force, 100%, the barrier is 0, right? That's this point. It shows how it crashes down as the force increases, like the red curve. Okay, so actually we will take a very short break so that I can have a break off to come. So the topic is quite timely in the sense today the subject of mechanochemistry is really upon us in the sense that, to say the least, you may wish that you have some kind of stress sensors. You may have some indication to learn about how stress develops in your system. So you want a chemical expression of how the forces in your chain, backbone, could become, could be measured. And this is certainly part of, in the spirit of capturing that type of, that kind of, you call it a reaction or not, basically it is a process that requires activation. Otherwise, so again, this obviously mechanochemistry, I think, is also important in the sense of sustainability, circularity of polymer chemistry and all that. because we're talking about how to degrade the polymer backward, right? So this is all, in that sense, intellectually very much related and a very important topic, therefore. And certainly this illustration of the things is not in any polymer physics textbooks. It's probably even rare. It's probably also rare to find in polymer chemistry textbooks. Let me know. I haven't done a search of that. I will definitely talk to my colleagues and see if I find out. So in any event, this is telling you that this age of the universe can be brought down very, very rapidly because it is in the exponential. So it turns out, if I express this properly, it's really just that your lifetime of the bond is now this barrier height that can vanish if there is enough force. Certainly, in fact, the next page shows you this is a calculation. This is a density functional theory calculation by the left. Look, I want you to pay attention to it. By now you're familiar with the concept of how much bond tension is in a bond, normalized by maximum, which was 6.9 nanonewtons. This, of course, is when you have no force. Look how long it's supposed to survive. Something like 10 to the 51 second. According to that calculation, it crashes down like this red curve. Look how, it's just mind-boggling. And I want you to pay attention to the part relevant to us. We are much shorter than universe, relevant to this part. Corresponding to something like 40% to 60% of the maximum force, you are bringing down the lifetime of your bond into your experimental window, meaning your experimental time scale. Going as much as 10 to the 7. What is 10 to the 7? It's about 100 days. It's over 100 days. You worry about your rubber or your polymer aging and fail in 100 days. So it's a meaningful number, okay? A year. All the way down to a fraction of a millisecond, which is perhaps the fastest you can capture something with. Now let me do a little thing that I hope you caught me when I say this. You will never be able to apply a force of maximum 6.9. Can you explain why? Well, you can if you can impose 6.9 nanonewtons of force on a time scale even shorter than this, then you can. So if I apply the force, let's say, the scales are just so huge, it's not funny. Any of this is 8th order magnitude. Okay? So if you impose whatever force, maximum you can, let's say, and you do it in 1 millisecond, a millisecond will break milli, right? It's somewhere here, 10 to the minus. It's somewhere here. Millisecond will only need 0.6 or 0.7 force to break. So you never need to apply that much before the lifetime of your bond is already reached. The rest, I'm not I'm not a big expert on this. Supposedly the chain breaking is quantum mechanical, so it's, there's probability associated with it, and so you have to do many to gather statistics. I'm not going to bother with any of that, except to just talk about the basic way to think about the effect of force on the bond. So the rest is not something I plan to go through. Basically, you can build a single chain model. You can, basically stretch it, just like this model I showed you here. Where do I have it now? Where do I have it here? This one. So basically, once it's straightened, you can see how much it builds, and then basically find out the force that you can achieve. And once you find out the force you can achieve, this diagram, for example, tells you how long your bond can survive. Okay, the rest is a bit of a challenge to do. So for a single chain, I think we appreciate the idea that the force will keep building. Once it's straightened, the bond can still extend a little bit, so that even though there's no coil to uncoil anymore, it's already straightened, you can continue to build force. And I mentioned about this force dictates the lifetime of your bond. But so it's fun to do some basic experiment to illustrate this. Pick up a single chain, do NFM, and make this measurement and learn about this. And in fact, I think I didn't even mention to you, depending on how you apply the force, you'll find the force it increases with how fast you stretch it in a log scale way. There's literature on this. I'm skipping it. But the problem is what we have is a network. I forgot the name, quadrillion. It's 10 to the 15. There's actually an English word for that. I just read an astronomy paper or news that says that. Quadrillion, something, you can Google it. So in any case, there are 10 to the 15 molecules. The story of one chain is not going to cut it. It's not going to. In fact, more importantly, it now speaks to the heart of. It really speaks about the difficulty of describing mechanics. Is how much we can speak about affine deformation. In other words, I don't have access to this chain, how much it's being stretched. I only have access, and then we assume we have. We assume this chain is the same as this rubber. Yeah? That's affine deformation. Yeah? That's the deep meaning of affine deformation. It is a tremendous approximation, and we dependent on it. When I double my rubber length, the end-to-end distance of the coil also just doubles it. That's what it means. Oh, Lord. There are too many parts that we have no time to go through. The basic point is perhaps just a little bit to share with you. Of course, is the fact that that the structure is heterogeneous. In other words, some strands can be very short. So when I stretch in this direction, some strands can easily straighten. I know I draw them evenly, but they are not. And some are so long, it never gets straightened during the stretching of this 10 to the 15 molecules. Okay? It just never will happen. Especially if you worry about building enough force such that it breaks, let's say, in 10 minutes or 1 minute. You can read the scale, find 1 minute is where. Huh? Yeah, you can definitely find, or you can go to your lab, take a cross-linked rubber, I'm going to stretch it, and I realize I'm stretching and breaking it in about, let's say, a minute or a second. Doesn't matter what you're comfortable choosing. Let's say a minute, it breaks. Looking at the scale, it says, oh, that means the force is about half of the maximum. Yeah, I'm just pretending. Yeah. And nothing happened before that, so you can stretch to a smaller number than 5 times, it doesn't break. So I think I'm not in a very good position to motivate the next plot, but I'm going to show it anyway to you. In fact, there is a place I explain this a little better, which is in a presentation that's already on YouTube. So what was suggested, what I was suggesting, was to pay attention, first of all, to this window. Our experiment will always be just in this window, right? 100 days to a millisecond. Therefore, I should worry about my force in the bond reaching this range. You with me, right? In other words, when I stretch a piece of rubber, no matter which day, who do it, since it breaks in a few days versus a few millisecond, it will involve a force of this range. Yeah? Do you agree on this? Huh? It doesn't involve a force here because that takes longer than universe. It doesn't involve here because it takes such a short time that I don't even manage to do that experiment. So do you agree? I don't know why it's so hard. Agree or not? I know I'm forcing you to agree. It's like, but there's that, you have to argue back to me. So turns out this point is absolutely critical. Because I initially didn't appreciate this point and got a different result, or different, less agreeable with the experiment result until I realized this. So what it means is I should build a relationship between, abandon this fine deformation, build a relationship between, look, the problem is very obvious. You want to have a sense of, because this is, microscopic lambda is all you have access to, yeah? That you agree. I don't get to the molecules and stretch them. I don't know. There are different distributions that oriented in all different directions too. So you have this. So how do I have a sense of how much tension is building in my chain? Number one, I want to convince you it doesn't build this way. That's a single chain behavior. And if you insist on using a fine deformation, indeed, this line would be true. But it's not. And I just said it should be involving chain tension in this range, 0.4 to 0.6. And furthermore, this is a bit of a wild speculation that I can guarantee you is correct. And we will have to do simulation, we'll have to do a few things to justify it. The point is this, as I said, a few chains, let's say, will quickly reach, let me see, that's not the right word. Let's say it reaches 0.4, 40% of maximum. Let's say, I don't have a calculation, I'm just pretend to you. Let's say that corresponds to a bond lifetime of, well, an hour, so 1,000 seconds, let's say. And you're going to break your sample in a minute, yeah? So 1,000 seconds is too long, meaning any bond that reaches this level of force will not break because it has 1,000 second lifetime to enjoy. But the next one is not even straightened yet. So what happens? This red chain, having a lifetime of 1,000 seconds, will wait. They move it around, the next green chain starts to stretch to this level again. And the next one does the same, and the next one does the same. And they wait and wait, they have 1,000 seconds to wait. And now you have enough chance of 1,000 seconds. If you stretch more, this population of chains will gain more force than 0.4. Okay? So I'm suggesting that I have to think about a population of chains gathering enough tension in them, and then they march on to higher tension and lower lifetime. A mouthful, what I said is to be captured by this red curve. This is untested, but I conjectured it to capture what I said. It will, no matter how you are growing your stretching, this is microscopic stretching, the rubber one. And forgive me, I can only imagine a population of bonds. I cannot imagine a wide distribution of bonds. I cannot treat this problem. So let me simplify it. Imagine there's a population of bonds that is doing what the red curve is doing. Look, the behavior is exactly the opposite of a single chain behavior. So, so it's lovely for me to say how madly this affine idea breaks down. Right? In its true sense. Because in both cases, I'm talking about the tension of a chain. And in both cases, I'm talking about your lambda is not your chain lambda. Right? It's in some sense. In any case, the rest of the story, watch. I designed a curve so that it attains a reasonable number of between 0.4 to 0.7 instead of 1. So first time I tried it all the way to 1. Remember, 1 occurs instantly, if force is 1. and it gives you a very weak capturing of this feature, so it doesn't work. In fact, I think I did more than what I planned to do, which was trying to sort of explain this weird proposal of red that never existed in the literature before, because the task never existed before, which is to explain elastomeric fracture. So I will, so we do have 10 minutes or so. I think I'm not pressed. It sounds like I have all the time I need to get your feedback and get this through. This is, let me tell you the whole motivation, or let me tell you how exciting this story is. In fact, as I said, I tried to I can verbalize this, but actually I had cartoons. So basically, I actually described this in an APS talk. Now it's available. I uploaded it to the YouTube, so I can provide you the link. A 12-minute talk that describes this entire story. The story goes as this. It is known since really, it's about almost 60, how do I say it? Nearly 70 years of the following story. It's in this place, it's a crime not to do rubber. I mean, I'm joking with you, right? At Akron, we were famous for doing rubber because of the historical achievement. So here's this a large story of rubber. Take a piece of cross-linked rubber, okay? If you hear from me for the first time, that's great. Take that piece of cross-linked rubber, hold in your hand, and you stretch, okay? It turns out I can take a minute to stretch until it breaks. Let's say it takes a minute. I stretch to this much. If I want to break the very same sample, I can make many samples, right? I'm going to do it in 3 seconds instead of a minute. I find I can stretch more before it breaks. Do you follow? When I use higher rate to stretch, I can stretch more, and therefore, of course, the force stress is also more, blah, blah, blah. That's one. Two, the same sample. Well, take your favorite part, SBR, so-called styrene butadiene rubber. The TG typically can be minus 50. Or you can take some part of the tire uses so-called butadiene rubber, just made of 1,4-butadiene. That TG is minus 100. Room temperature is rubbery, of course, because it's way above TG. So room temperature, again, let's say I use 10 seconds. Stretch there and break. Make your numbers. Let's say I stretch 3 times, it break. Lower the temperature. Let's say you do it at 0 degrees, or even minus 10, still way above TG. You'll find your rubber stretches much more. So these two features, known for nearly 70 years. Textbooks are written on the phenomenology, and I will skip talking about how it is explained. I would only go as far as telling you it's not explained. It's not explained. Let me be absolutely accurate on this. You could throw a word, well, since it's cross-linked, you could, of course, throw a word. Anyone should throw a word by saying, by the time I rupture, there must be some chain broken, yeah? It's crazy not to think so. But the two features I just showed you, I indicated to you verbally, was explained for 70 years without involving the concept of chain breaking. Meaning, it was not recognized that chain breaking plays the dominant role or even is relevant. Can you accept that? Huh? In fact, I think you got so much background information by now. It's assignment that I will send you the link that you watch that 13-minute of APS. You should be so proud because this is the not only it's frontier research, it is at a level accessible to you, but also at a level that is the highest in the business. There, I even explain very gently, without spending actually even a minute, about what is going wrong. What was the textbook explanation? Well, I did say what's the textbook explanation. I don't plan to say much here. But watching that APS talk, you may get a slight sense of what that textbook explanation is, except I apologize because we haven't talked about time-temperature superposition yet. Maybe after that we will review it again because that talk speaks about so-called WLF shift to acknowledge your internal clock is temperature dependent. And there was some tremendous confusion about the thing that you learned so well so far, that is relaxation time being temperature dependent. And somehow people thought that is explaining why the rubber was able to stretch more at a lower temperature. And that's not the case at all, according to what we can clearly visualize and understand today. Yes?
So when you said if you stretch a sample quickly, it is able to stretch more, that is because more chains are able to break? Is that what you're saying?
You see, English word because is a very careful word. I will never use it so freely. When you use it because, you are talking about causality. You know what I mean, cause and effect. So I know you can you rephrase it, because the reason I want you to rephrase it is because you use the word because involve potentially suggesting confusion about causality. So because is not something you used in science often, because it means you are saying something is leading to something. So rephrase it. I'm sure the rephrase, yeah, to verbalize what you are trying to, yeah.
So if you are stretching the sample faster,
You stretch more.
why is it able to stretch? Yeah.
Why?
Why is it able to stretch more?
That's the million-dollar question. No, what do you mean? What I mean is that phenomenon is what we know for 70 years. Answering why is exactly the whole point. So, we.
You're saying that it has not been explained in terms of the bond
Correct.
breaking so far, but that should be considered.
To me, that's all there is. Okay, you're bringing home the whole point. Look, you got a dear polymer that's permanently cross-linked, and you stretch it and it will break. Remember that movie, that the fast melt movie, I said it's like a cross-link? Sharply break it. How on earth that breaking has nothing to do with the fact that create a path where all the chains are breaking? Of course they are, right? And the funny part is the earlier theories about it even mumbled the word chain breaking into the description, because of course you have that. There's nothing funny about the fact a chain breaking happens. The question is using this event of chain breaking to explain this, right? That did not happen. But since I spoke probably by now 20 times the word bound lifetime, can you not explain? Let me rephrase it for you. When I break let's say I have my student prepare 20 samples, so I can just take 20 samples and do them. I take one, I'm going to use 1 minute to break it. Boom, it breaks. But now I'm going to be impatient, I'm going to use 3 seconds to break it. Okay? You hear me clearly. 1 minute is 60 seconds. 3 seconds to break it means I'm using a time 20 times faster. So what is happening here? So think very loud. Yeah, so I'm sure you're getting there. So let's imagine the following. Let's say in the 1 minute breaking, it involves a force of, let's say, 50% of maximum. Okay, it's just a translation, right? You read it, yeah. So let's say it takes 50% of maximum force. Corresponding to that, it breaks in a minute. Yeah? Let's again assume that when I do it fast, I also first reach 0.5. But I spend the time, instead of a minute to reach 0.5, I spend only 2 seconds to reach 0.5. Okay? So I reach the same bound force. Would it break? Okay, let me rephrase it. When you say I break slow, when you say I break my polymer, my cross-linked rubber, in 1 minute, reaching force of 0.5, it means my bond roughly has a lifetime of a minute. Is that reasonable? Roughly. Now, I'm going to draw it much faster. So for example, that breaking occurs at lambda equals 3. Now, which give you 0.5. Now I'm going to draw much faster. Do I need 1 minute to draw to 0.3? To draw it to 3 times? Of course not. You're going to be 20 times faster. Therefore, by the time you stretch to 3, corresponding to 0.5, you have spent only 2 seconds. We just said at that point the bond lifetime is a minute. So would it break? Then what? Remember, your goal is to break it. Then what? Oh, come on, please. It only took me 2 seconds to reach 0.5. At that time, my bond lifetime is a minute. It's still happily living. So what? Then what? I didn't ask you to stop. I didn't. How much simpler can I get? I'm just stretching out. I'm closing my eyes. I'm just stretching. I'm just using a rate that's 20 times faster. I can do it with my eyes closed. Yes, it will keep triple the length. My bond lifetime is still a minute. I only spent 2 seconds. You keep stretching, and it's a vicious feedback loop. You keep stretching, you are starting to build more force, and the lifetime crashes down. See? Crashes down, and now it becomes 10 seconds. No, the force is still not high enough. It crashes down more as you stretch more, the force builds more. Until 3 seconds, the lifetime is about the time you spend. That's my last slide, last point, which is this curve. So this is showing the lifetime as function of f. That's these 3 curves. And these horizontal curves are the rate you use. And the solution is the point when your bond lifetime equals your stretching time. Okay? This is as new as only a few weeks old. Of a problem that's 70 years old. Of a leading problem. In fact, today, I tell you how important this problem is. Remember, we are today in the, certainly in the issue of sustainability, circularity of chemistry, and then there's environment. What the environment are we talking about? Pay attention to the next lecture, Whitby lecture, who is going to talk about this. We're talking about your tire, automobile tire, over the years, losing weight, generating microparticles that some of us may embrace and cause health problems. How can that cross-link tire lose weight? Well, you are. Erosion, you are breaking them, right? You're breaking the chains, you're breaking this. Okay, so yes, I mean, you have more chance to stretch more if you're doing fast. Ultimately, to the leading order, it's the lifetime coming to match your experimental time. Which, by the way, of course, is a function of how much you are stretching. Both are function of how much you're stretching. Lambda, the nominal lambda. And lambda, all in this figure, relates to f. So it's all about, in both cases, they are functions of f. And this graph is just solving the solutions for the f. And then you put it back into lambda so you can get a description of the fact you can stretch more. So this, I'm surprised we went through all this today. It's very dense. I had no idea we were finishing it up at all. So I don't know what else to say. Maybe you can say I'm very fluent, but maybe you can say I'm less prepared. I'm joking, but essentially I couldn't. So I didn't prepare the next slides, which was to give a prediction on this. So chew on this. It's a very basic problem. I told you the 2 things. Now you understand the rate. Of course, the temperature is the second point I mentioned. And the reason temperature comes in, just in a nutshell, is because, where is it? I know I have this expression. Sorry, where do I can surely write it here again. This lifetime sensitively depend on temperature. The T0 there. So it depends on how much thermal energy is available to cause you to hop over the barrier. Okay, we're done for the day.